you have to do 3 different limits, right? But otherwise, it's the same thing. All right, that's good. How about continuity? Does anybody remember the definition of continuity of a function? You remember it? Yeah. You want So if we say that a function f of x is continuous at x equals a, this means what?
F of x equals a, for f exists at a, the limit exists at a, and a equal each other.
Exactly. So to say that a function, back in Cal 1, to say that a function, f, I should technically say f, but I'll say, to say a function is continuous at x equals a means that the limit as x approaches a of the function is equal to the function's value at a. And all this means visually is that if you have a here, that your function approaching a from the left and from the right is approaching the same place. Okay, so that right there with an open hole would mean that that limit exists, right? Because the left and right go to the same place. But if you fill that hole in with the function itself, then it's continuous. So you basically can draw it without picking up your pencil. Well, with vector valued functions, the idea of continuity is pretty much identical. It says that we will say that a vector valued function r is continuous at a if the limit as t approaches a of the vector valued function is equal to the the vector function's value at a. So again, this is exactly the same thing, right? It's that you're drawing this thing in 3-dimensional space or 2-dimensional space. As you come in from both sides, you're headed towards the same. Yeah, but remember, our limit is a vector, right? So it's drawing these vectors that are pointing here, pointing here. So these vectors are trying to point to the same place, right? And then when we get there, we fill it in with the vector that is the value of the function. Just remember, when we're drawing these things, we're drawing curves, but we're drawing them with vectors, right? It's not an actual like point moving through. It's the tip of the vector moving through the space. So these vectors are approaching something, and then at that value of a, we have the vector there filling it in. So very, very similar to what we saw in Cal 1. This is just kind of just to throw it in here. I'm not quite sure why I put that in there. But can you tell me just by looking at that what that would draw? That is a vector function, isn't it? Yes. It's 3-dimensional. What is that going to draw? It's just a line, okay? So we've already seen this, right? This is linear, this is linear, this is linear. So this should draw our line. So this is actually that couch potato. That's the couch potato formula. I should take that out of there. I don't know why it's there. Oh, well, maybe this will help. I would like us to find a vector function that draws just this line segment. Okay, so this is different than what we've done in the past. If I gave you 2 points, you could come up with the vector equation of the line through the 2 points that keeps on going in both directions. This time, I want you to only draw the segment of the line that goes from there to there. All right? So here's the way that I am going to teach you, if you haven't seen this before, how to do this. We want to go from here to here. So this is an important word here. I want us to start out at 3, 5, 9 and end at -5, 7, -3. So what I'm going to do is I'm going to use this because it's a line segment. All right? My R naught is always going to be where I start, converted to a vector. So nothing is new, right? I mean, this is all, that's stuff we've done. Now, the next part is the direction vector, which is going to be the vector that goes from here to here. So what is that vector? -8, 2, -12, right? Okay, that would draw the whole line, wouldn't it? But I don't want to draw the whole line. So what I'm going to do now is I'm going to restrict my domain. And what do you think I should restrict my domain to be? So t here, I'm going to restrict it between two different values so I can start it and stop it. 0 and 1. Okay, so it will always be 0 and 1 if you set it up the way that I set it up. I always use R0 as where I start, right? And then this right here must be the direction vector connecting the points. All right? As long as you set it up this way, where this is your starting point and this is the vector that goes from the starting point to the ending point, then you'll always just use the restriction 0, 1. And you can check it yourself if you plug in 0 for t, right? This is all gone, and here's where you are. And if you plug in 1 for t, that's just going to be this vector added to this vector. If you add those together, you'll get that vector. And then every value of t in between will just take you along the line segment. All right? All right, finally get to something a little more interesting. I've always liked this sort of problem. Because I think if you look at this problem initially, I think it might be something that's a little bit challenging. So what we have here are two cylinders. One is a little bit smaller than the other. All right? I would really like to know, if I give you the equation of those cylinders, if you can draw me the curve of intersection. So can you come up with the R of t that would draw me those curves? Right? Does that seem like that might be a little bit bumpy, a little rough to come up with that? You raising your hand? Let me give you the functions. There they are. So I'll give you two cylinders. Were you raising? No? Oh, okay. Wow. How in the hell are we going to do this? Do you all understand what we're trying to do?
Yes.
Okay. Why would this be useful? Let's say that my company is in charge of welding pipes together, right? I need to somehow program a computer to weld this for me, right? I need the actual curve. I need to be able to program the robot to kind of draw that shape as it welds, right? So I need to come up with a function that would do that, right? Or maybe I need to know the length of that curve because I need to know how much material I'm going to need to do the welding. There's a lot of different things I could be asking. But we first need the actual curve. So let me go back. Does anyone have an idea of how to do it? Because I'm going to try and give you a hint here, but I want to make sure. Okay, so if this is the intersection of these two cylinders, then we're looking for the x, the y, and the z that would work for both of these at the same time, right? So all the points on that intersection have to satisfy these two simultaneously. So you're saying set them equal to one another, right? Okay, if we do that, let's try it. Let's just go with that. If I set them equal to one another, how do you want me to do it? Solve this one for y squared maybe? And then plug that in over there and try that? Okay, everyone understand what we're going after here? Okay, so let's solve this one for y squared. The y squared equals 9 minus x squared. We're going to go ahead and take that and we will plug that into this one over here. So that's going to go into that. I know that looks ridiculous, but y squared is 9 minus x squared and then plus z squared, right? Equals 4. So what do we get here? Z squared minus x squared. I'll just put it in that order. Oh, no, I don't like that, but -5. We've got that, right? Okay. And what is this? What is that? So the problem is we have three unknowns, right? And we have two equations. So I think you have the right idea that if we're going to draw this, it has to satisfy both of these simultaneously, right? So we're on the right track, but that algebra is kind of messy. I'm going to go back here. There's the picture, right? I want you to focus your attention on something here. Let me bring the cylinders back in here for you. Just slightly bring them in. Okay, so yeah, you can see those enough, right? All right, I'm just going to rotate this, and let's just look at it this way. What can you tell me about those curves kind of in that direction? They're circles, right? Because look, they have to live on one of the cylinders, right? So from this perspective, which I believe we're looking down the y-axis, if I'm not mistaken, I have to go back and look at the equations. Let me look at the equations real quick again. We had x squared plus y squared equals 9, and we had y squared plus z squared equals 4. So this is the bigger one, right? And the z is free here, so this one opens like that. This one is missing the x, right? So it was actually coming out the x-axis. So when I go back here, that's actually the x, so it should be rotated. This is more like kind of the way we've been looking at them. X-axis, y-axis, z-axis. So if we look at it from the perspective here down the x-axis, those are circles, right? And those circles are actually coming from this one right here, right? Agreed? So can you draw circles? Can you draw a circle of radius 2? Using a vector function, not a x squared plus y squared equals r squared, not one of these standard equations of a circle. Can you draw me an equation with a vector valued function? And we just talked about that, didn't we? So r of t equals, here's what we know. We know that to draw a circle in the yz plane, right? In the yz plane, my x is free, right? And so I'm only going to be working with the y and z components. So what should these two component functions be to draw me a circle of radius? What's my radius over there? 2. So what do I put here and here? 2 cosine t and 2 sine t. So before, when we used cosine t, sine t, that drew me the unit circle, right? But putting a 2 in front will draw me a circle of radius 2. So that should draw me this circle. Now what I need to do is be worried about this back and forth, right? Because as I draw the circle, my x is moving, right? It's moving. You look at it from the side, right? As I'm trying to draw that circle, my x is coming out and in as I draw, right? So what's dictating that? What's dictating the in and out? Let me look at it from the top. That in and out is dictated by the bigger cylinder, right?
Yes.
Okay, so here's the equation of the bigger cylinder. Right here. That's dictating my in and out. And all I need to know is what is the x component, right? What's the x component? But to be on the bigger cylinder also, that means all I have to do is take this and solve it for x. Okay, so solve this for x. Let's solve that for x, and what do we get? X is equal to root 9 minus y squared, but plus or minus, right? Well, does it make sense that we're going to have two answers? Because look, we have two different curves, don't we? So this x should be plus or minus square root of 9 minus y squared, right? But we can't put y squared in here because then this wouldn't be a function of t anymore, would it? It would have t's and it would have y's. So I put 2 cosine t because this is y, right? That's what y has to be. So that is going to replace this y right here. So that's going to become 4 cosine squared t?
Yes.
Right? So when we take this y and square it, we get 4 cosine squared t. Ugh. Okay. Plus or minus square root of 9 minus 4 cosine squared t, and then 2 cosine t, and then 2 sine t. There we go. And really, I only need my t to go between 0 and 2 pi right now. And that should draw me the whole circle. Right? Just one. And if I do the plus and minus, it should draw me both sides. Does that make sense? So it's kind of like when you were saying like you want to set them equal to each other. We did that, but what we did first is we drew first like one thing we knew about one perspective, which was the circle. We got that set, and then we let that x-coordinate be dictated by having to satisfy this. So we satisfied this with the 2 cosine t, 2 sine t, and satisfied this with the square root thing. And there it is. Make sense? Okay. Now, when it comes to vector valued functions, computers are pretty useful. So you can kind of take a, here we're just going to take a look at some kind of weird ones. So this one's called a toroidal spiral. Y'all know what a torus is? You ever heard of a torus before? It's basically a donut. A torus is a donut. I doubt anyone has taken any topology, right? Not topography, but topology. Y'all ever heard of topology? It's a math subject. So if you take a flat sheet and you were to take this edge and put them together, right? You get a cylinder. Okay, and then imagine that I also, as I put these two edges together, I put these two edges together. So if I did that, and then these two edges come together, you get a torus, okay, which is a donut, all right? It's just a donut. That's called a torus. Now this is a toroidal spiral. It's a spiral going around a torus. So look at the vector valued function for this. Do I not list it? No, it's in here. There it is. This particular one, here's the first component function. It's 4 plus sine of 20, I use r instead of t, 4 plus sine of 20r times cosine of r, and then here's the y component function, and then here's your z component function, and if you plug that into a computer, it will draw your toroidal spiral for you. All right, this is just showing you how technology is useful to be able to graph things like this. Here's another one, trefoil knot. This is a vector valued function that ties a knot into itself. So it kind of like goes into itself and ties a knot. So it has its own vector valued function. This is the vector valued function right there. All right, finally, derivatives now. How are we doing here? Wow, still got a ways to go. So I've got great news when it comes to derivatives of vector valued functions. You know how the limit of a vector valued function, you just do the limit of each component? Same with derivatives. It's awesome. If you want to take the derivative of a vector valued function, we're using the prime notation here. The derivative of a vector valued function is just the derivative of each component function individually. Awesome. Now, if your component function has a product in it, then you have to do the product rule. Or if it has a chain rule, you have to do a chain rule. But you don't have, you can just, this is its own world, that's its own world, you do them separately, okay? And that goes for 2 or 3 dimensional vectors, vector functions. Now, what is the geometric meaning of the derivative of a vector valued function? So back in Cal 1, if we had some curve, right, f, and we were to say, go to some value a here, go here, and then tell me what is the derivative of that function at a, what does that represent? What about the tangent line? It's not, it doesn't give you the tangent line, it gives you the slope of that line, right? So this right here the slope of that line, right? The slope of that tangent line is equal to the derivative of that function at A. So all it does is gives you a pitch of a line, right? That's what the derivative does here. But in vector valued functions, when you take the derivative of a vector function, I'm going to go backwards here. When you take the derivative of a vector function, you get a vector as an answer. Do you see that? You take the derivative of each component function, but your answer still lives in the brackets, or the angle braces, so you are, or angle brackets is what they like to call them. This is still a vector, right? So that's not a slope of a tangent line anymore, right? So here, what I've done here is in black here, this is going to be the vector function. So remember, as we let t go, it's going to draw, this black vector is drawing the curve, right? So that's r of t. And what I've plotted with this is its derivative, which is another vector, right? And what I've done is I've attached it to the tip. I've taken the tail of r prime and I've attached it to the tip of r. And you can see then that if you move that around, it looks like a tangent vector, doesn't it? Doesn't it look like that vector is tangent to the curve, right? So it is giving you a vector tangent to your curve, but there's something also that's changing. Do y'all see something that's changing as this time goes on? It's getting what? So look at it there. Look at its length. Do you see its length there? Didn't it look like it was getting longer as we went? So we know with vectors, there are two things that are important when it comes to vectors: direction and length, right? Magnitude and length, or sorry, magnitude and direction are the main characteristics of a vector. So there's a lot of information that's being stored in this red vector derivative vector. So if r prime is a vector function, oh, I went too far. I need to go back. Sorry, I was like, why are we talking about that already? So r prime of t is a vector function, right? We start with the vector function, we take its derivative, and we get a new vector function. If we're given a value of t, then r prime of t is a vector which is tangent to the curve at the point r of t. So that's what hopefully I just tried to show you with that example, or with a visual. So this one we're going to actually do. So we want to find the derivative of this, and then we want to find the vector that's tangent to it at a certain point, and then the vector equation of the line. So we're going to do these one at a time. Let's start with that. So first, find the derivative of this vector function. Okay, here we go, one at a time. So what is the derivative of that first component function? Sine t plus t cosine t. So we have to break out the product rule there, right? And then on the next part, we're going to get cosine t minus t sine t. So product rule, product rule. So notice the derivative is a new vector function, right? This is a new vector function. So that answers the first part. Next part of this, find the vector that is tangent to that function at t equals pi over 2. So that's just asking us to find r prime of pi over 2. So all we have to do is just plug pi over 2 into this. So what is sine of pi over 2? 1. And then what is cosine of pi over 2? 0. So that's going to be gone. So this is just 1 comma, and then cosine of pi over 2 was 0, and sine of pi over 2 was 1, but then we have a pi over 2 in front, right? So minus pi over 2 here. All right. So at t equals pi over 2, the vector that would be tangent to this curve would be the vector 1, negative pi over 2. The last thing is for us to find the vector equation of the tangent line. All right. So what is different between this question and the one just before it? Yeah, this actually wants the vector equation of a line, doesn't it? The previous one just wanted to know what's the actual tangent vector at pi over 2. So it's like we have a curve that's being drawn. This is r of t. Sorry, r of t. Terrible. That's r of t. And then what we did is we found a vector at pi over 2, right? We found that vector. And what we're asked for now is give me the vector equation of the entire line that corresponds to that vector. So what formula will we use for this? Yep, this one right here, right? Vector equation of a line. We're trying to find the vector equation of this line, which means we need two things, right? We need a point that we're going to start at and a direction vector. What point are we going to start at? That's this point right here, right? But that lives on the original curve. So what do we need to compute to find that? Plug in pi over 2 into the original, right? So what is r of pi over 2? That will give us this point. And then what about a direction vector for this? How about a direction vector for this line? Well, that's this, right? That's this. This is a vector that is pointing in that direction. So this right here will be our v, and the r naught we had to go back to the original curve to get. So here's r. Let's plug pi over 2 into that. I believe we get, what, pi over 2 into that. We should just get pi over 2 and then 0. So this is our r naught. And then this right here is going to be our direction vector of our line, v, and we just put them together. Does that make sense or not? Yeah? Yeah? You got one? So this is kind of like in Cal 1, you were asked to find, they would give you a function, they say, hey, find the derivative at this point. And then they say, find the equation of the tangent line at that point, which was a little bit more work. We can find the derivative of that function at a certain point, but we can go one step further and ask for the vector equation of the line that's tangent to the curve at that point. So our final result, r of t, this is going to be our tangent line, is going to be r naught plus t times v, which is 1 negative pi over 2. And then we could put those together, but I'll leave them. All right, there's a concept that we're going to be using later that we definitely did not do in Cal 1 when we were talking about tangents, and that is this concept of a unit tangent vector. So we've already looked at in the past that if somebody gives us a vector, right? If we ever have a vector, as long as it's a non-zero vector, we can always find a vector that points in the same direction but has a length of 1. And all we did was we took the vector and divided it by its own length, right? Well, we're going to do the same thing here because it's going to become useful later for us to use this vector. We are going to recognize that back in this picture, when we were finding that red vector, which was the derivative, right? The derivative vector, that as we moved, it was changing its length, wasn't it? But we can always find a vector that would point in the same direction, but it would maintain a length of 1 the whole time. And so that is called the unit tangent vector. And so we just need to make sure we understand visually what it is and then mechanically how to get it. So if r prime is a vector function, then its derivative is a vector. And so to find a unit vector in the same direction, which we call the unit tangent vector, and we use capital T to denote it, we just take the vector, the derivative vector, and divide it by its own length. So it's a pretty straightforward computation. So for the problem we just did, what would be capital T of pi over 2? Well, this by definition is r prime of t, or sorry, r prime of pi over 2 divided by the magnitude of r prime of pi over 2. And what was r prime pi over 2 again? What was it? Was it 1 negative pi over 2?
Yes.
Was it? Okay, it was 1 negative pi over 2. And we want to divide that by its own length, which would be the square root of 1 plus pi squared over 4. So we just square that, add them together, take the square root. Which if we write it all in one vector, it would look like this. 1 over square root of 1 plus pi squared over 4, comma, negative pi over 2 over square root of 1 plus pi squared over 4. So this vector right here should point in the same direction as that vector, but it should have a length of 1. Why don't you all take the next 10 minutes to get this one. Y'all can work together on it, but to kind of break up the monotony of me just sitting up here talking, why don't y'all try and work this one out? Just make sure everyone can do this mechanically. Give you a vector valued function, it's 3-dimensional. Want to find the vector equation of the line that is tangent to that curve at this point. So this problem is a little bit different than the previous one, but let's see if y'all can figure out how it's different and how to proceed through it. All right? All right, I'm gonna step out for a minute because usually when I step out, y'all start talking. Who thinks they have it? Does anyone think they have it? We just need a calculator?
It's just a general, the variable. I think we use that. So there's no like value one, it doesn't say T. At that point, T is equal to two, first one is the whole equation.
I think you have it right. I think you have it right. Let me see. Pi over 2 cosine of 1 pi over 2. Yeah. Okay. This is good. So, shall we talk? Yeah, it's been, well, no, it hasn't quite been 8 minutes, but visually, here's what we've got. We've got a curve in three-dimensional space, right? We've got some point here, the point 0, 1 pi over 2 is where we are, and we're trying to look at the tangent line to this, and we're trying to come up with the equation of that, right? Well, you're going to need to know, first of all, a point on that line. And the point on the line, you're kind of given, right? Yes. You've already given that point on the line. So right away I know R naught is equal to the vector 0, 1 pi over 2. But now you need the derivative vector. So I need to be able to come up with this vector that is tangent to this curve at that point. Well, that means first I need the derivative vector function, right? So just take the derivative of that. R prime of t equals, what do we got here? Negative 2 sine t, cosine t, 1, right? So this right here, this is a function that will spit out this blue vector, but what do I have to provide to it for it to be able to spit out a vector? I need to provide it with t, which means I need to know, remember, like this is drawn in three-dimensional space. This right here, that vector r of t, right, is the vector that gets me to that point, this point right here. Which means you have to figure out what t is that gets you to this point on this original function. So what t, and it's kind of obvious once you look at it, what t would I need to plug in here to get me to this? Pi over 2. Right? If I plug in pi over 2, cosine of pi over 2 is 0, so that's 0. Plug in pi over 2 here, sine of pi over 2 is 1, and then of course pi over 2 there. So that you can just do by visual inspection. So the time in question here, the time that we're talking about is t is pi over 2. And so now we plug that into our derivative. And that will spit out this vector. So sine of pi over 2 is going to be 1, so negative 2, and then cosine of pi over 2 is 0, and then 1. So there we go. So that now back over here, our direction vector, v, is negative 2, 0, 1. Does that make more sense now? This question was a little bit tricky in the sense I didn't give you t. Like you had to recover t from the point. Yeah?
How do we do that if it wasn't like
obvious?
Visually? Yeah.
You'd have 3 equations and 3 unknowns, right? You would have this has to be equal to 0, that has to be equal to 1, and that has to be equal to this, right? Now you'd have 3 equations, 3 unknowns, but they would not necessarily be linear equations. So you couldn't use matrices unless they were linear equations. Most likely they're not. So then you would just do kind of hope that one of them is doable, right? Right, because when you think about it, look at this. Right here, if I did this right here, just that equals that. 2 cosine t equals 0. That would mean that cosine t has to be 0, and that has an infinite number of solutions, right? And then same with this one, sine of t equals 1, infinite number of solutions, but you would try and figure out, which overlap, because you have this, you would have sine of t equals 1, so that does limit some of your answers, right? If you have to do both of these simultaneously, right? So what are all the answers to this one? I like to use a unit circle. Where's cosine 0? It's going to be here and here, right? Like at pi over 2 or at 3 pi over 2 or any pi multiple. But this one, this only has solutions where? At the top. And so you could throw these out. So now you have basically an infinite number of solutions, but you've narrowed them down to just the ones up here. And then this last equation, well, this was the one that gave it away, right? This is telling you what t has to be, right? So it is possible you could have more than one solution. It's possible that it could be harder to get them. All right. So what we just did was that was the curve, okay? And we went to pi over 2. And we found the equation of that dotted line. So we found the equation of that dotted line. All right, second derivatives. So we did, see, we're just kind of like just going through the same thing we did in calculus, right? Limit, continuity, first derivative. What does it mean visually? What is it? And now second derivative. So the second derivative is just the derivative of the derivative. Yeah, okay, great. But we have something additional in here that we didn't have in calculus 1, and that is this idea of smooth. So a vector function r of t given on some interval I, so if we have some curve, 3-dimensional or 2-dimensional space, and we have it defined on some interval, so we start it and stop it, then we will say that it is smooth on this curve, on this interval, if first of all the derivative is continuous. So that means that when you take the derivative, it is well defined on this curve. So within this interval, you don't have any, like division by 0 or square roots of negative numbers. So long as the derivative of the vector function is well defined, and the derivative is not 0, not the 0 vector, except at the endpoints, then we will say it's smooth. That's weird, right? Because, I don't know if it's weird to you, but like in Cal 1, what did the second derivative being 0 in Cal 1, when was that useful? Like what were we doing in Cal 1 when we would look at second derivatives being 0? That had to do with concavity, right? So I'm going to draw you a picture of a basic curve from Cal 1. Here and here, our first derivative would have been 0, right? But right here, that's where our second derivative would have been 0, because we would have had this inflection point, right? This change in concavity. Here, with vector functions, we're going to say our vector function is smooth so long as the first derivative is not 0. Like if the first derivative is 0, right? Back here, it was just like, that's where we found like max and mins. But here, when first derivatives are 0, it somehow messes up the smoothness of our graph. So let's look at a specific example and kind of see what's happening. So take a look at this one right here. The question is this vector function smooth for every t in the real number system? So what am I checking to say it's smooth or not?
We're checking whether it's continuous and whether there are any maximums or minimums.
We're checking make sure the derivative is continuous,
Yes.
and make sure that the derivative is never 0. Okay, so let's take a look at the derivative first of all. The derivative of this, well, we do derivative of each one, right? So that's going to be a little chain rule. Y'all agree with that? Okay. And then 4t cubed. All right, so is this a continuous function on all real numbers? Well, that's continuous and that's continuous, right? The product of two continuous functions is continuous. So this is continuous. That's continuous because it's a polynomial. So this is a nice, well-defined function, right? Now, the next question is this derivative ever equal to the 0 vector? I'm sorry, is it ever equal? I meant to say, is it ever equal to the 0 vector? Is there a value of t that I could plug in that would cause any sort of problems and give me the 0 vector? What value of t? 0, right? Is that the only value of t that would give me the 0 vector? Remember, the 0 vector is the vector, in this case, because it's two-dimensional, would have to be 0, comma 0, right? So you need both components 0 at the same time. So the only way to make that one 0 is if t is 0. There's no other way. There's an infinite number of ways to make that 0, but there's only one that makes them both 0 at the same time. So at t equals what? At t equals 0, we have the 0 vector. So that means there's something wrong at 0 in terms of smoothness. We're not smooth at 0. Y'all want to see the picture? Okay, let's look at the graph and see why we say it's not smooth. So here's the picture of this two-dimensional vector function. There it is. It's like a cusp, right? But see, now we're either in 2 or 3-dimensional space and we don't have the whole idea of vertical line test anymore. So these cusps could be happening anywhere. So, imagine something going through, and then it does something like that in 3-dimensional space. That would be kind of like a cusp and we'd lose the smoothness. And that test, the test for smoothness is where's the derivative of the vector function equal to the 0 vector? So I have this little animation here. What I can do is I can play it for you. And what I want you to pay attention to is the derivative of the vector function. All right, so I'm going to back this thing up. And I want you to just pay attention. What's happening there? So look at the derivative. So what happened right there? Look at the direction. It's like a massive change in direction of that, right? It's like you're pointed this way, and then in an instant, you are now pointed back this way, right? And that right there is what messes up your smoothness. Had this done something more like this, we would have smooth, because it would be a nice continuous transition like this. But the cusp messes up our smoothness, and the check for that, the thing that will tell you, is that your derivative of the vector function will give you the 0 vector there. And that's because it has to, if it changes direction, it's going to have to, if it's continuous, it has to like slowly move through 0. Okay, so not slowly move, but it has to continuously move through 0 to change direction. All right. Some properties of derivatives. I keep on having this question in my mind of why y'all signed up for 8 weeks Cal 3. And then I'm asking myself, why did I sign up for 8-week Cal 3? We still have them. There's 5-week Cal 3. Can you believe that?
There
How do you
is.
do that? I mean, just sitting there for that long in a classroom is... Well, don't they do it like every day? I think they do it like 4 days a week or something. So it's like, yeah, it's a little better. This is like drinking water through a fire hydrant. Okay, differentiation rules. So we have these rules are really important when it comes to the derivative of vector functions. But the good news is I think everything's going to look very familiar to you. So let's say you have 2 vector functions. So instead of like r of t, I'm using u of t and v of t. So 2 vector functions. And they're being added together, and you want to take the derivative with respect to time. Well, good news. You just take derivative of each one separately, right? So that's like your standard rule from Cal 1. And if you change this to minus, that's minus, right? Okay. The derivative of a constant times a vector function, the constant just comes out and just comes along for the ride, which is the same way it was in Cal 1. So that's all good still. What is this? The derivative of, what is that and that? Because these are not the same. That's a vector function, right? What do we call a function now that's not a vector function? We call them scalar functions. Okay, so now we have two classifications. We have vector functions, which involve vectors, and then our standard functions from everything we've done before are called scalar functions. So if you take a scalar function times a vector function, and you want to take the derivative, look at what it is. Does that look familiar? That's your product rule. So let me give you an example of this one. If I want to take the derivative with respect to time of, let's say, sine of t times the vector function t squared t plus 1, right? So here's a scalar function in front of a vector function, right? This says that, well, you could just multiply this through, okay, and then take the derivative of each one separately, or each component separately, or you could just use this little product rule, which would mean that you take the derivative of the scalar function, which is what? Cosine t, right? Cosine t times what? The vector function t squared t plus 1, and then plus the scalar function sine t times the derivative of the vector function, which would be 2t 1. Okay, now if you put this cosine through and this sine through and then put the two vectors together, you would get the same result as if you had put these through first and then just did them individually. All right, so this is how you deal with a scalar times a vector function. Just do your product rule. Look at this one. If you have two vector functions dotted together, because you can dot two vectors, right? So if I have a vector function dotted with another vector function, if I want to take the derivative of that dot product, it's this. And what does that look like? Product rule again, right? Look, I mean, this is a product, right? But this is more like a scalar product, and we wind up using the product rule. This is a product, but it's the dot product, and you wind up using the product rule. And then look at the last one. It is a product, but it is a cross product, and guess what you do? The product rule, but now the product is different. See, here it's multiplication, multiplication. Here it's dot product, dot product. Here it's cross product, cross product. But it's still the same thing. Derivative of the first one times the second one. It's just the operation's different. So these are nice properties. The last one, what rule is that? That's your chain rule. So if you have a vector function and inside of it you have a scalar function and you want to take the derivative, then you take the derivative of the vector function, evaluate it at the scalar function, scalar multiplication times the derivative of what's inside. So when we get to an example of that, I'll show it to you. I'll kind of say, hey, that's property 6 if we do it, all right? All right, we're gonna try and wrap this up here. We might end a little early. I'm not going to go past this section, and we're getting close to the end, but these last two examples can take a little while. All right, read that, and then let's think about it. Do something with it. I just thought of something. When I gave y'all 8 minutes, I stepped out. I hope I muted my microphone. There's this video I saw on YouTube where this like a city council meeting, you know, and one of the guys is up there and he has to take a bathroom break in the middle of the meeting. And he steps out and it's like over the whole intercom during the whole thing, you can hear him go in the restroom. It's hilarious. I'm pretty sure I muted it. Oh well. All right, show that if we have this vector function that r of t is orthogonal to r prime of t for all t. So what this is saying is that for this particular vector function, the vector that draws the curve is always orthogonal to the tangent to the curve. Visually, I think we can all agree because of what it's drawing. What is it drawing? A circle. So I think we can all agree with this, right? If we draw this, as we draw that, the derivative vector is always orthogonal to the vector function itself. But let's prove it. So how would we prove this? I mean, visually, I think it's self-explanatory, but how do we prove this without the picture? Yeah, we have to show this, right? What we need to do is we want to show, I don't know if you've ever seen that before. That stands for want to show. Mathematicians like to use that a lot, WTS, okay? We want to show that r of t dotted with its own derivative is equal to 0, right? Not the zero vector, the number 0. All right, so let's do that. What's r of t? It's cosine t sine t, right? And we dot that with what? Its derivative. What is its derivative? Negative sine t cosine t. All right, let's go ahead and figure out what that is. So we're asking ourselves, is that 0, right? So when we dot that, we get negative cosine t sine t, and then plus, same thing, right? Sine t, cosine, doesn't matter what order you put those in. And that is 0, isn't it? They just cancel each other out. And that's it, we've shown it. It's nothing complicated there, right? Y'all agree? So if somebody hands you a vector function and asks you to verify whether or not it's always orthogonal to its derivative, all you'd have to do is check that the dot product is 0, right? Okay, now look at this one. This is the one that is tough. Not many students can get this one. So I think I'm going to just let you think about it for about 3 minutes. Oops, I went the wrong way with this. And I don't say that with any disrespect. I don't think I've ever had anyone get this in class. So it would be surprising if someone did, but I'll give you time to think about it. So all it's saying is that show that if you have the magnitude of a vector function is c, which is a constant, then r of t is orthogonal to its derivative always.